ionic bond, there's a lot of ways to describe it. First, let's start by describing it based upon which elements come together. A metal and a nonmetal. Recall that staircase is the divider between metals and nonmetals. Again, the term ionic compound was referenced in the flame test lab. But now we can really go over you understanding what they were. So again, we go over this because you have just seen on that sheet that ions are typically more stable. However, when we wrote down Na+1, sodium can't just lose its electron to nothing. Just like chlorine, Cl-1 can't gain an electron from nothing. The two have to work together. So a metal and a nonmetal work together. And in doing so, they create a type of bond. Another way to refer to an ionic bond is it's between a cation and an anion. Again, that first term is not cation. Cat is a prefix used in chemistry to refer to positive things. In AP Chemistry, we're going over the cathode of batteries right now and the anode of batteries. Because the root word in both those terms is the word ion. It ends in I-O-N. Now, Maddie was thinking to herself, okay, more vocabulary. I have to memorize what a cation is and an anion is. How do I do that? You ready, Maddie-O? The cation is positive. I heard a deep sigh, which meant, ooh, that was pretty corny. I think I heard someone kind of breathe heavily, like maybe that was kind of funny. Michaela, that was good stuff right there. Cation, positive. Anion's negative. Sorry, there's no good way to do that. Although the term anion has an N at the start, just like negative has a start. An example. The simplest ionic compound is sodium chloride. So table salt. In sodium chloride, it's a combination of Na+, and since it's the positive ion, it's the cation, and Cl-, the negative ion. So again, slide number 1, a little bit of vocabulary. What's a cation? What's an anion? These are terms we need you to be aware of. But then we're introducing this new thing called an ionic bond. That you just saw that ion forms are more stable because they have a full outer shell of electrons. Well, you'll have two different things with ions coming together to form this type of bond. I say it's a bond, but it's really more of opposite charges attracting. And this is something that comes up a lot in chemistry. That rule of magnets that you learned in elementary school applies to a lot of the laws of chemistry. What holds sodium to chlorine is the fact that sodium is a positive charge and chlorine is a minus charge. They attract one another, they hold together. We now have salt crystals. Another example, so there's one example, opposites attract Na+ and Cl-. I can give you a second example. Not every ionic compound is one metal to one nonmetal. Calcium chloride, CaCl2, were the white Dippin' Dots type things that we left in the cabinet overnight in Unit 1, and then they looked all melty the next day. That was an ionic compound. It was an ionic compound that when you expose it to the air, it absorbs the moisture in the air. So no matter what the formula is, it's always a matter of opposite charged particles attracting one another. So again, an ionic compound is a metal and a nonmetal. Something with a positive charge, metal. Something with a negative charge, nonmetal. And they're able to hold together because of that opposites attract rule. My last slide then is to remind you of hopefully what we just went over with that sheet of why are there ions in the first place? Ions form because of the octet rule. This octet rule is really big in chemistry. For a Chem 1 student, you will be referencing the octet rule an awful lot during the course of the year. Now I say atoms strive for a stable octet. I am kind of using personification, giving personal qualities to non-living things. Again, atom of fluorine just doesn't go around thinking, man, I could really go for an electron right now to get up to 8. Or sodium doesn't go around thinking, boy, if I can only lose this one electron, I'd be such a better person. How they get to that octet is based upon the trends of the periodic table. Non-metals have high electronegativity, so they have a tendency to gain electrons to get to that stable octet. And once they have a full shell, think about electron configuration. Once you have a full shell, if you were to lose an electron, you're now stable. Happens to be a full shell is 8 outer electrons. So that's why it's called the octet. Although helium, for example, is stable with 2 because it's the first shell. Keep in mind, to obtain the octet, it's based upon electrons being gained or lost. Protons in the nucleus never change when you form an ion. You don't obtain a positive charge by gaining a proton. The nucleus remains unchanged. It's the electrons. So an example would be sodium can lose 1 electron to be isoelectronic with neon. Neon's a noble gas. There's a reason why shorthand notation is based upon noble gases, because noble gases are stable. They have a full outer shell. If sodium loses an electron, it becomes a positive charge. However, you can't just lose an electron to nothing. Sodium can't just decide, I got to get rid of this electron, man, I don't like it. There's got to be something around that's willing to gain that electron. So chlorine could gain that electron. It's a nonmetal with a high electronegativity. If it does, it's isoelectronic with argon, another noble gas. So in essence, what's happening is sodium is going to give an electron to chlorine. They both benefit from this relationship now. It's like a symbiotic relationship in a biology class. That one gives, the other receives. Stability is having a full outer shell. When I cracked open sodium metal at the start of class and did the demonstration with it, sodium metal is highly reactive because it is not stable with 1 outer electron. It wants to lose that 1 outer electron to have a stable octet. That means it's going to change. It's going to react. You saw the reaction. You heard the fizzing of the reaction. Like the beaker with water in it is now pink from that indicator to show that it actually reacted as well. So there was a reaction that took place to make that happen. The last slide of notes isn't anything that you're going to write in your notebook. I actually want you to draw on your periodic table again. So when you get this written down, if you could have out your periodic table. One of the things that we find helpful for students is to have them write at the top of the columns what charges would these elements have to lose enough electrons to become stable. For example, above the first group of the periodic table, I want you to write a big old +1. Because every element, kind of excluding hydrogen, in that first column, if it loses 1 electron, it's now a noble gas configuration. Just like in the second column, beryllium on down to radium, I want you to write a big +2. Because if beryllium were to lose 2 electrons, it would be like helium, a noble gas, a full outer shell. If barium were to lose 2 electrons, 1, 2, it'd be like xenon, a noble gas. Now the tricky part is the middle of the periodic table doesn't work out nice and neat, because that d orbital makes things weird. So we're going to skip that altogether. Feel free to write a +3 above the boron on down column, although that one is a little goofy too because you're crossing that staircase, metal, non-metal barrier. I'm not going to have you write anything above the carbon column. because it's difficult for carbon to gain 4 electrons or lose 4 electrons. However, I want you to write a -3 above the nitrogen column, a -2 above the oxygen column, and a -1 above the fluorine column. Metals, elements to the left of that staircase, will try to obtain the octet by losing electrons. Nonmetals, elements to the right of the staircase, will gain electrons to achieve the octet. It would be difficult for fluorine to lose 7 electrons. 1, 2, 3, 4, 5, 6, 7. To get at the octet. It's actually very easy for fluorine to gain 1 electron to get to the octet, however. So that's why metals and nonmetals, how they get to that stability is different. Last thing I want you to do is, if you haven't done it already, let's make sure that we highlight that staircase. That divider between metals and nonmetals. And you could just pencil it in a little bit more. But that staircase on the right-hand side that starts between boron and aluminum and works its way down. Let's make sure we indicate that we know that as well. Our goals today is to show you that octet rule, that rule of stability. Elements will either gain or lose electrons to have noble gas configuration. Once we know that, we can now introduce to you how we can give the names of these compounds. Because if you recall, when I was going over the lab with you, I wasn't reading out the formula of things, I was saying their name instead. Some people will refer to NaCl as just NaCl, but we'd usually just call it sodium chloride. So now that we have an introduction to what is an ionic compound, we need to start going over how to name these compounds. On the way in, we picked up a worksheet that says binary nomenclature type 1 ionic. I would like you to have that out in front of you. I'm going to write the first 3 examples here on the smartboard. An ionic compound, for the most part, consists of a metal, which is the first element, and a nonmetal, which is the second element. Remember, metals to the left of the staircase, nonmetals to the right of the staircase. How we would name them, I give you 3 naming rules on the top. It says, rule number 1, you're combining a metal with a nonmetal. Rule number 2, name the cation, the metal, first. Do not change the name of the element. So in other words, if I look at this first problem up here of CaCl2, Ca stands for calcium. Just like in the second problem, BaS, Ba stands for barium. Cs stands for cesium. So when you're naming a formula for an ionic compound, the first element symbol is just its normal name. Rule number 3 says name the anion, the nonmetal, second. Keep the beginning of the element the same, but replace the ending with I. In other words, I do not call CaCl2 calcium chlorine. I call it calcium chloride. Making it end in the I shows that it's bonded. So it's not just 2 elements around each other, there are 2 that are now combined. So instead of barium sulfur, BaS would be barium sulfide. Instead of cesium nitrogen, it would be cesium nitride. Why don't you take a minute to answer the last four on that front side. The NaCl, the MgO, the BeI2, and the SR3P2. And the metal name is just what it normally is. The non-metal, make it end in I. Spec. What's the name of NaCl? Sodium chloride. Charlie M, MgO. Magnesium oxide. Cat, BeI2. Beryllium iodide. Brooklyn, SR3P2. Strontium phosphide. Now, if you call it phosphoride, I'd be fine with that. You're ending in I, that's the important part. Hopefully, that is one of the most simple things that we do in chemistry all year, where all you have to do is make the second thing end in I, right? I have to cover one more part of this, though, before we can move on. And that's the fact that some of these elements have subscripts with them. So, for example, there's a 2 here. There's a 3 here. Scroll further down, there's a 3 and a 2 on this last one. There's a reason for that. And what I want to do, now maybe this is going to be like on the right-hand side of your worksheet. I'm going to give you 4 more problems right now that we're going to do together to explain this. But instead of giving you the formula, I'm going to give you the written name. You need to be able to start with a formula and give the written name, which is what we just did, which again, hopefully is pretty easy. Make the second thing end in I. The trickier part is if you're given a written name, you have to figure out the formula for it. So we're going to do these 4 example problems right now to wrap up class to go over that. If I gave you the formula or the written name potassium oxide, I would want you to tell me what the formula is. In order to do that, I would first write down the symbol and the charges for these things. So Alyssa, what is the symbol for potassium? K. And Alyssa, if you look at the top of that column, what charge would potassium normally have to be stable? +1. Alec, what's oxygen's symbol and charge? O and -2. In an ionic compound, you have a metal and a nonmetal. Metals lose electrons, nonmetals gain electrons. They work together. However, the number of electrons gained and lost have to balance each other out. Right now, I have potassium losing 1 electron and oxygen gaining 2 electrons. It doesn't make sense. What we do is we use subscripts. Remember back here, subscripts to represent how many of each element do we need in order to make it balanced, so there's no overall charge. So in other words, the formula of potassium oxide, does anyone have a guess of what it should be to balance out those charges? How many potassiums do I need? How many oxygens do I need? What do we think? Close. K2O. That subscript after the K means I need 2 potassiums. Because if I have a second potassium, I now have a +2 charge and a -2 charge. The two balance each other out, which means my electrons gained must be my electrons lost. So again, as we do these problems, you need to know the charges of the elements and then figure out the formula. Let's look at the next one, aluminum fluoride. Tyler, what's the symbol and charge for aluminum? Al, and what's its charge? +3. Tess, fluorine, what is its symbol and charge? F and -1. These charges don't balance. That means I need subscripts in order to balance them out. Do I need more aluminums? Do I need more fluorines? Who thinks they know the formula for aluminum fluoride? Baron. AlF3. 3 fluorides will now give me a -3 to balance out my +3. 2 to go. Barium. Sulf. Symbol and charge for barium. Ba +2. Be would be beryllium. Randy. Nitrogen.
-3.
Again, if you don't recall, where are we getting these charges? We wrote them at the top of the column of our periodic table because those are the charges that those elements would need to be stable. The entire point of an ionic compound is metals and nonmetals work together by gaining and losing electrons from each other so they can both be stable. This formula is a little more tricky. Ba3, N2. If I have 3 bariums, I'd have a +6 charge. If I had 2 nitrogens, I'd have a -6 charge. They balance each other out. There has to be a balance in charges. That way electrons gained and lost equal. Last problem. Paige, beryllium, symbol and charge. Be +2. Noah, selenium.
-2.
And what's its symbol?
Fe.
Do these charges balance each other out? Yeah. BeSe would be the formula. There's one last thing I want to leave you with. When we look at these 4 problems, the reason why we have subscripts is to balance out charges. So electrons gained equals electrons lost. Everyone's at their stable octet. When you are writing formulas, you can think about that every time, or there is a simpler method to solve this. Are we ready? We're looking up here. You take the charge of the metal, ignoring the positive part, just the number part, and you're going to make it the subscript for the nonmetal. You take the charge of the nonmetal, ignoring the minus part, and you make it the subscript for the other part. It's called cross and drop. If you take that charge and make it the subscript for the other part, that 2 now is behind the K. Look at the second problem if we did that. 3. You don't actually have to write down the 1 because it's assumed to be 1 because you wrote down the element. Look at the barium nitride, the trickiest one. Put the 2 behind the N, put the 3 behind the Ba. Now in this last one, the charge is already balanced, so we would not call it Be2Se2. But that cross and drop method is a way to solve this. I believe when I wrote down pages in your textbook for homework, again, when I do that every day, that's more of a reference. So if the naming system doesn't make sense to you, you can use the pages in your book to look up this exact same thing.